Ready to get back to some linear algebra, right? All right, let's take a look at the warm-up. So we're talking about a transformation, T of x, which is multiplication by our matrix here. So T is a transformation. It's a mapping from a space to a space. In this case, it's a mapping from what space to what space? How would we describe the mapping before we actually start answering the question here? From a space to a space. From R3? There's going to be an R3 involved. What's the other one that's going to be involved? R3 is going to be in there somewhere. R4 is going to be in there somewhere. From which one to which one? Remember, when you get stuck on that, I mean, it's hard to remember here. There's an M, there's an N, which one is which. What I really suggest you do is write out some vector x that you're going to multiply to get some vector v. How big does this thing have to be right here to actually be able to do this multiplication? 4, absolutely. This has to be x1, x2, x3, and x4. Because they got to line up with each one of those columns. So where does x live as a vector? It lives in R4. So this is a mapping from R4 to somewhere else. Well, one way to think of that multiplication would be to take the linear combination of these columns of A. So x1 times this vector, plus x2 times this vector, so on and so forth. But if I'm adding up a bunch of those three-dimensional vectors, I'll end up with a three-dimensional vector. So I'm going from R4 to R3. Any questions about that? All right, so we're mapping from R4 to R3 with this matrix multiplication process, mapping x to some b. And so the question is it one-to-one, is it onto? Let's start with onto. Is it onto? That means, can I get to any b in R3? That's one way to restate that question, is it onto? Can I get to every single possible b? Another way to say that would be, do the columns span R3? Right? Is there some linear combination getting me any vector in R3? And how do we tell in this case? Is this one onto? What's the easiest visual way to check this thing?
See this is variable.
There is a free variable here, but that doesn't necessarily mean it's going to be onto. What did you say?
A pivot in every row.
Pivot in every row, absolutely. There's a pivot in every row. So I have a pivot position here, here, here. As long as there's a pivot position for every row, then I'm good. So that's a big check, so this one is onto. Now a visual representation of onto. All right. So this is one way to maybe visualize it. I was talking with a student and suggested this was a good visual model. And so I have a book. My book's sitting there on the table. I might say, is this paper on top of the book? And I might just kind of lay it down like that on it sideways. Is it on the book? Sort of. It's half on, it's half on. Right? Part of it's being covered by the paper, part of it's not being covered. So if I put it all the way so it's completely covering this book, then I would kind of describe it as onto. It's definitely on the book now. Right? So every single piece of my book is being covered by that piece of paper. That's another way to think of this idea of onto. Is that every element in R3 I can get to or is being covered by some image of X. Any questions about that? As you're going through some of this material, I'm going to give you different ways to think about it. If you have your own way to think about it that I haven't talked about, let me know about it, because it could definitely be helpful for other students. I'm always looking for new ways to explain stuff or think about stuff. Are any questions about onto? Then we go one-to-one. So is it one-to-one? That would be the next question here. So what is this saying here? This says, is they're at most 1x such that ax equals b. Is there a unique solution here? Are the columns linearly independent? That's another way to think about that one. And what's our visual way to check this one? To see if this thing is 1-to-1.
Column.
Pivot in every column, absolutely. Is there a pivot in every column? Is that true for this one? For this one up here? I don't have a pivot for that fourth column. Okay, 4 columns, pivot here, here, and here. But there is no pivot in this column. So this is not 1-to-1. And another way you can think of this one is in terms of the free variables. Right, if there are solutions and there are free variables, it can't be 1-to-1. Right, because then I could choose different parameters to get to that same output value. Okay. Once again, some of these we can look at just by the dimensions of that matrix A. Right, this matrix is going to be a 3x4. There are too many columns for this one to be 1-to-1. There's no way this one could be 1-to-1 just by looking at it. All right, any questions about 1-to-1? All right, in the second one, what about this one? 1-to-1, onto, both, neither. What do we get for this one? Neither. Confirm, deny. Everyone seem happy with neither? A couple nods here. I would agree here. So let's put this thing in row reduced form, or just row echelon form. I'll have 1, 2. I'll take this second row minus 2 times the first row. I'll get 0, 0. And I'll take the third row plus the first row. I will once again get 0, 0. So this is the row echelon form. There's only one pivot position. It's right here. So there's not a pivot position for every row. There's not a pivot position for every column. So it's neither. Not 1-to-1 or onto. All right, any questions about the warm-up? All right. All right, so our plan for today is take any questions you might have from Chapter 1 that we've gone through so far. After that, we're going to get into Section 2.1. We're really going to get into matrices this time, matrix operations. That's what 2, 1, 2, and 3 are about. After that, just a reminder for tomorrow, or statement for tomorrow, we're going to have a Chapter 1 quiz tomorrow. So I'll cover all the content that we've covered from Chapter 1, and to get us warmed up for that exam that's coming up next week, I believe. All right, so questions. Any questions from Chapter 1? Any questions? How is the homework going? Are we still enjoying the Pearson? Is it still reasonable? Would you suggest it for a future use? Yep.
I think the examples really help. Like it helps break down the problem step by step.
Good. There's certainly a lot less questions for me from homework. Usually I get quite a few that we work through in class. So I'm just assuming that the examples are helping and then the multiple attempts helps. And I guess the test will be exam 1, right? Okay. All right, well, if there's no questions, we will get on to Section 2.1. So from 2.1, I have a list of kind of the big topics from this section. As usual, whenever we start a new topic, it's going to be terminology. Right? So we're going to have to talk about what it means for a matrix to be n by n. We've talked about that one a little bit. We're also talking about the elements being little m sub little n. Talk about what diagonal elements are, what a diagonal matrix is. We talk about the basic matrix operations, how to add, subtract, and do all that stuff. We'll pick up some properties so we can do a little bit of algebra with the matrices. We'll talk about matrix multiplication and look at some of those properties, and last we'll talk about the transpose. So those are the big topics. As I was not so subtle about last class, this is a good chapter for a reading quiz, so that's what we're going to have, a reading quiz real quick. So you can close your book and close your notes. And pass it out. It's designed to be comprehensive. That's the master section 2.1. That's what class is for. This is supposed to be to go through the reading and do a decent job of skimming through the material in the biggest stages. All right, so just the front here, we've got three matrices you're going to use to answer the questions. State the values, so identify some elements, do a little bit of matrix addition. Number two, we're just talking about matrix equality. What does it mean for two matrices to be equal? And last one is a little bit of algebra. If you have any questions about the notation or any questions at all, make sure you raise your hand. And this is a quiz, so make sure we're keeping our eyes on our own paper and doing our own work. So just so we don't overthink things, write down the values if they exist. Whenever you're done, just flip them over so I know you're done. All right, we're gonna pass them all over here. Make sure your name is on them, of course.
You didn't have one, though.
What?
What is on Thursday? You didn't have one.
What's on this list?
You told us on Thursday you didn't have
I have all the prep quizzes here. All right, so once again, big idea here is just to make sure that we're really going through the reading, because I think it's really an important part of the process. Previewing all that content before we get to the class is just a good way to be exposed, and it makes the lesson make a lot more sense. So I'll go through the first couple here. We have our matrices A, B, and C. What about A? What is the 1-2 element of the matrix A? 0, right? And probably too nice of a matrix because you could have them mixed up and you get the same answer, right? But this says the first row, second column. Same thing with B here. It's hard to mess that one up. But it's the 1-1 element, so that one's also 0 here.
That's this one.
This one right here. First one was 1-2. This one, however, you have to make sure you have them right. If we're looking for the second row, third column, what's this value? It is no value. It does not exist, right? There is no third column of C, so it does not exist. Or whatever you want to write there, right? There is no value here. Go to A plus 2B. Well, we have the matrix A, 1, 0, 1, 0, 2, 0, 0, 2, 0, 0, negative 1, 1, plus 2 times B. Well, 2 times the matrix just says that we're going to multiply each element, or each piece, each component of that matrix by the value 2. So I'd have 0, 2, 0, 0, 2, 2, 0, 0, 2. When I multiply a matrix by a scalar, that's what I do. When I add two matrices together, I just add up their components. So this is going to be 1, 2, 1, 0, 4, 2, 0, negative 1, and 3. I just add their components together here. What about A plus C? Can't do it. Right? Does not exist or can't do it or whatever you want to write here. Because when we talked about matrix addition, we talked about adding two matrices of the same size. They have to have the same dimensions to do this addition. Now in application, it's perfectly reasonable to want to add the elements like this. But we just don't add these matrices. We would augment C and make it the same size by maybe adding zeros and whatever missing spots there are. But just adding these two matrices, we can't do it. Okay? Any questions about those first ones? All right. For what the values of A and B is A equal to this thing? Well, we got to kind of skim up here to our matrix A, which is A is equal to 1, 0, 1, 0, 2, 0, 0, negative 1, 1. So what does it mean for two matrices to be equal to each other? It means they have the same value in all their components. So what would little a be?
0.
0. What would b be?
1.
1. Okay. That seems a little almost cheesy, right? And in the past, some students will get this wrong because it seems too easy, right? The purpose here is to understand formally what it means for two matrices to be equal. We know what it means for two numbers to be equal. Right? When x equals 3, x is 3, right? We know what it means for those things to be equal. We have to define what it means for two matrices to be equal. All right, find a matrix D such that 2A plus D equals B. This is a little algebraic kind of equation here. So there's a couple things I could do. I could multiply both sides by 1/2. That might be a reasonable way to start. I get A plus D equals 1/2 B. Then I could maybe say, well, if A is 1, 0, 1, 0, 2, 0, 0, negative 1, 1, plus some matrix D is equal to 1/2 of B. So I'll take B and multiply by 1/2. We'll get zeros, 1/2, 1/2, 0, 0, 1/2, 1/2. And then what should I do?
Subtract A.
I can subtract A to the other side. I'll get this matrix minus that matrix. That's just plus a negative, so I can just subtract each of the values in the components. I will get 0 minus 1, so I will get minus 1 here. 1/2 minus 1, 0, oops, 0. 1/2 minus 2 is a negative 3/2. 1/2, 0, positive 1, and negative 1/2. All right, any questions from the preparation quiz here? Any questions about adding and subtracting these matrices, multiplying them by numbers? Okay. All right, so where does that get us here on our list of things we want to be able to do? Matrix terminology. Now we understand that this means the M row, N column. What is a diagonal element? It's the ones that are on this diagonal right here. So specifically, if I'm talking about in terms of this notation, A to what would be on the diagonal? 2, 2. Right? Because I have the same row, same column, that identifies all these diagonal spots. Now, if the matrix has zeros everywhere else and only values on that diagonal, then we call it a diagonal matrix. We've also talked about our basic matrix operations. So we did all this kind of stuff in the warm-up quiz. And we also kind of talked about a lot of our properties. But now I want to be a little more specific. So we're basically the spot where we can do matrix properties. And essentially we just did a whole bunch of these. Right? We just solved an equation that looked like this. And to do that we had to use a whole bunch of properties. So let's see, we started off by going like this. But we certainly could have also said this is 2A plus 2D equals B. That would have been another way to kind of go about the solution process. But once again, to do that step, we know that we can do that with real numbers, but can we do that with matrices? Well, these properties essentially tell us that we can. And of course, we could prove all these properties, and it would just be like how we did with vectors. All it is about writing out the definitions. We have a definition for matrix addition, and we have a definition for taking a scalar value times a matrix. Those are the only things we have defined for us. Now, the rest of these properties is just about using those two definitions and the properties for real numbers. So if we wanted to define this thing, all we would do is take these two matrices in general terms, say what is a matrix addition? We write them all added together. What does it mean to multiply them by a scalar? And the result would look like the same thing. So it would really be the same kind of proofs you did with these vector properties as well. Now that we have these properties, we can do the things that make sense for our matrix equations. Right, without looking at the properties, we kind of knew that we wanted to distribute the 2 and then subtract the 2a, or however we want to go through the solution process. That all made sense to us. These properties tell us that, yeah, it makes sense and we really can do it. Now, of course, these properties all have fancy names, and you've probably seen these names a couple times. I'm not going to necessarily quiz you on the names, but the more you see them, the more they should sink in, and the higher up in mathematics you get, the more you'll need to know them by name. So the first property is the commutative property. Commutative property of addition. So it doesn't matter which order we do the addition. The next property is called, anybody know this one? Associative property. Associative property. Once again, of addition. The next one's a little trickier. It's the additive identity. Additive identity. It's an identity property. It means we think of it as we add something and we're not changing its identity. That's one way maybe you can think of it and have the name make a little bit of sense here. So if I have A, I add 0 to it, I still have A. So the additive identity property says there is something called 0. In this case, it's a matrix full of zeros. But there does exist something where when you take A and add to it this 0 thing, this additive identity, you just stick with the original value. What's the next property called?
Distributive.
Yeah, we have the distributive property. Distributive property. Then we have another kind of distributive property. So really both of these are distributive properties. It says scalar multiplication distributes over matrix addition. And then you say scalar addition distributes over multiplication, I guess. But they're both forms of the distributive property. What about the last one? The last one is just an associative property again, but for scalar multiplication. I'm actually going to add one more. I'm going to add one that says there exists, there's my backwards E for there exists, something that we're going to denote with this, negative A. There exists some matrix that looks like this, such that A plus this special matrix that I'm calling negative A gives me what? 0, right? So this is just kind of call it a formality, but it's an important piece here that there really is this thing that I can add to A to get 0. Now in general, we might not know what this special thing is. We can kind of guess what it is here for matrices. What is that thing?
The opposite.
It's just negative 1 times A, right? If I take A times it by negative 1, I'm going to get negative A. Right, so this is just kind of a formality here in this case, but it's important to include it, I guess. Right, so this thing is called the inverse, the additive inverse. And this is really actually an important one, because when we went through and solved this 2A, 2 times quantity A plus D equals B, there's some things that we did that we probably did really quick without really thinking about. So when we got to maybe 2A plus 2D equals B, if I wanted to solve it this way, what's my next step? I'm at this step, I want to solve for D. What do I have to do next? Subtract 2A, right? You can subtract that 2A to the other side. And that's what we say. We say we're going to subtract 2A from both sides. But really what we're doing is we're saying, I know there exists something. There exists something I'm going to call minus 2A. And I can add that thing to both sides without changing the value of, let's say, negative 2A. Without changing the value of the equation. And I can add that element because I know it exists. And when it exists, I know that the sum of those two things is 0. So that's me using the additive inverse. And then furthermore, I'm using the additive identity property to say that 0 plus 2D is actually 2D. Now, of course, we don't actually do any of that stuff. But if we wanted to actually prove that this process was true, those are the steps we have to justify using our properties. Okay, any questions about that? If you ever go through a formal proof class, that's the kind of thing you have to prove the properties of real numbers. You have to go through these steps of really being careful and saying, why can't I subtract 2 from both sides? Well, I have these properties that I can start from. Okay. So the next big topic was matrix multiplication. Let's go back before we go forward. Recall for matrix vector multiplication that we had 2 ways of doing this. We had 2 ways of taking matrix times a vector. We could do the row vector multiplication, this, where we're talking about the dot product, which we'll talk more about later, but it sounds like most people have seen it before, of our first row and our vector. Right, so we're taking this product plus this product plus this product. That's going to be our first line up here. And we kind of keep doing that. And we visually took this vector and kind of, if I had, said if I had that vector like this, we kind of visualize it as going like that, and then taking this product plus this product plus this product is the first term, and then this product plus this product, that product, and so on and so forth, working our way down to get this new vector here. We also said we could do matrix multiplication and think about it as a linear combination. We had our linear combination idea. Now why are we reviewing that? Well, because matrix multiplication is just kind of an extension of matrix vector multiplication. You can think about it that way, or you can think about it as matrix vector multiplication is just a special case of matrix multiplication. Either way kind of applies. But think about it as just multiplying a whole bunch of vectors. Think about taking the product of A times each column as a vector to get a new matrix like this. All right, so I have some matrix B. I'm going to think about it just in terms of its columns. So I'll have those columns, a vector here, and a vector here. I can really think of it as a new matrix where it's A times that first column as the new first column, A times the second column is the second column, and A times the third column. All right, so let's do a couple here. All right, so for the first one, I'll do it one way here, and then you guys can get started on the next one. Once again, a couple ways I can do this. I can think of this matrix A times the first column here. So I can think of this as 2 times 1 plus 1 times 0. And then kind of going down, 2 times 0 plus 1 times 3, and 2 times 0 plus 1 times 2. That would all be the first column of this product. Maybe I should call this one X instead. Matrix B. Or some other matrix. And then I take A times the next column. So I will get 0 times 1 plus 0 times 3, 0 times 0 plus 1 times 3, 0 times 0 plus 2 times 3. And I'll simplify everything and get 2. And then 0 plus 3 and 0 plus 2. 0 plus 0, 0 plus 3, and 0 plus 6. Any questions about that process? Of course, check my work to make sure I didn't mess up any of my addition here. All right, so go ahead and do the rest of them here. Do the next 2 as practice, and we'll compare our answers and see what we got and make sure we have this mechanical process now. It really is just a mechanical process. The fact that each got to do a whole bunch. Find a nice way for yourself to visualize the process.
The second entry in the first column would be 0%.
The second entry in the first column, yes, it should be. Thank you. Right here. I'm taking this times this. 2 times 0 plus 1 times 1. One right there. Thank you. Oops. Look through that homework online. I encourage you to keep a notebook as you work through that, so you have a reference for those problems to study for, quizzes for exams for. So keep a nice record of your work. Means when you do matrix multiplications, sometimes these problems can get kind of big. So just plan for that kind of space, just like it was for linear systems. All right. So the other thing, of course, I'm demonstrating here is we can check our work with Mathematica. So we have a couple ways to do that. One, I can just enter in these matrices directly. So I enter them as a list of the rows. So it's a list of a list. So I have my curly braces kind of used up here already. I put the semicolons at the end so that I don't have to see the output. I'm just storing them to A and B. And to multiply them, I use the dot here. So A dot B is matrix multiplication. So not a space like you're multiplying numbers. That would give you a different answer. So if I left the space here, and say what? So make sure you have a dot there to do matrix multiplication. You can also, of course, use that other notation, enter it, where I'm using control comma to go to new elements of the row, and control return to go to new rows. And just put a dot in between them. And that should also give me a value. I'll get that value, once again, as a matrix, as a list of rows. If I want the pretty value, I can always use matrix form, either after the result or before the result, like I did up here as a command. So is that what we got? 2, 2, 3, 5, 1, 2. Any questions about that one? Let's take a look at that one. 2, 2, 3, 5, 1, 2. All right, so I'm going to take this thing times the first one. I'll get 2 plus 0 plus 0 plus 0. And I'll go down to this next one, which is this product here. So I'll get 0 plus 1 plus 0 plus 4. So 1 plus 4 is 5. And we kind of shift over. We do this column times the first row. We get 1 plus 0 plus 1 plus 0, 2. And we'll get 0 plus 0 plus 1 plus 0. So far we're on line. Yep, we are. And once again, we shift over, taking this column and this row. And we'll get 3 plus 0 plus 0 plus 0, so 3. And lastly, this combination gets us 0 plus 0 plus 0 plus 2. Okay, that's kind of half visual, half talking it out. Any questions about the process? Any question where any of those values came from? Make sure if you have questions, you ask. All right, then what about the last one? I can't do it. Well, I keep talking about, okay, well, let's start with taking this first column. There's only one column in this case, so it's like matrix vector multiplication. And I can't do it. There's not enough columns in the matrix. So the dimensions here are going to be important. Sometimes the dimensions are going to be such that we can't do it. There have to be the correct number of rows of the second one to match the correct number of columns in the first one. So let's talk about that a little bit more here. Let's look at number 2. What's the dimension of that first matrix? It's a 2 by 4 matrix, that first one. What about the second matrix? What's that one? A 4 by 3 matrix. So now what about those dimensions tell us that we can do the multiplication? Absolutely. We need to make sure that the number of rows over here, well, that's the number of rows, has to match up with the number of columns here. That's the number of columns. So these inside values have to match for us to do the multiplication. Those inside values have to be the same. Now what about the dimensions of the result here? What's that last matrix? This is a 2 by 3. Those are the outside values. So these inside values tell us whether we can do the multiplication or we can't, and these outside values should match the dimension of the output, final result. And it's just a nice quick check. Right, so you do your matrix multiplication. If you made some sort of weird mistake along the way, the dimensions might not match up. So it's a quick thing you can look at the end to make sure you're doing the process right. Okay, so let's generalize it here. All right, if I have a 4 by 2 and a 2 by 3, I do the product. What am I going to get for the dimensions of my final product here? 4 by 3. What about if I take B times A? What should those dimensions be? I can't do that multiplication, right? Because this would be a 2 by 3, and this is a 4 by 2. Now those inside values don't match. So in that case, I can't do that multiplication. Now right away, that tells us something about matrix multiplication. That's pretty important. What's that?
Order matters.
Order absolutely matters. Order absolutely matters. So AB is not always equal to BA. In this case, we can't even do it. But even if we could do it, it might not lead us to the same result. All right, so now we're going to get into matrix properties here. It's a big important one being the first one. That's not commutative. Matrix multiplication is not commutative. So we took for granted about matrix addition. Yeah, we can do the matrix algebra. We add them, subtract them. We can't take things for granted now. There are going to be some things that just seem natural that aren't going to be true anymore. So let's look at our properties. We do have some of the other basic ones. We have associativity. We have a distributive property. We have also a different distributive property. What's the difference here and here? How come we have two distributive properties? Aren't these kind of the same thing? They're not the same thing because order matters. Right? They're very careful when we write these. A times the quantity B plus C is A times B plus A times C. The A is in front of both these cases because the order matters. So can we do distributive from the other side? I don't know. Because multiplication isn't commutative, that's not necessarily a given. Turns out we can do it, but once again, now the A is on the right-hand side because it was on the right-hand side here. So order matters. Okay. Then we have the associativity of scalar multiplication. It doesn't really matter where we multiply the C by, it's going to be okay. And last thing, we have an identity property. So this is the multiplicative identity. There is a 1. We have 1 times 4 is 4, right? We have some number in real numbers where I take 1 times any number, I get just that number. We have the same thing for matrices. It's that identity matrix, where it's just 1s along the diagonal and 0s everywhere else. So I have a 1, so 1 times A is A, and so it should work the other way, that A times 1 is also A. I have to be a little bit careful. Why is this one M and why is this one N? What's going on with the M and the N? That makes my statement. The size matters, right? If A is an M by N, the identity has to be the right size to multiply it on this side. On this side, it might be a different size over here. Okay, so there is an identity that you multiply on the left to give it A, and there is one on the right. It just might be a little different size. So there is a 1 there. So most of the properties are the same, but the commutativity is a big problem. All right, so some other kind of quick statement notes here. Powers of a matrix. It's really more of a definition than anything here. A cubed is just A times A times A. So that's all it is kind of by definition. And A raised to the 0 power, just like 2 raised to the 0 power is 1, A raised to the 0 power is this identity. Now the one question about that is that if you're going to look at A cubed, that really only makes sense if A is a specific kind of matrix. Right? If A is a M by N, and I'm multiplying it by itself, what's true about the size of A? M has to be equal to N. This has to be a square matrix for this to work. Okay, so this only applies to square matrices when we're talking about powers. All right, so we're really just stating a definition there. And we have another definition here, the transpose of a matrix. The transpose is just the elements of A with the rows and columns swapped. Right, we're tipping it on its side. All right, so there's our fancy kind of definition in terms of the little subscript things. But really, to see what it is, we have to just write it out once. So here's my matrix A, and now I want to write out what A transpose is. Well, if I switch the row and the column of 1, it just stays that spot because the rows and the columns are the same. But if I take this element, which is the first row, second column, so this is A first row, second column, I'm going to move this one. This one is going to get moved to, in the transpose, the second row, first column. I'm going to switch the rows and the columns. What that's essentially going to do is take this spot and map it to this spot. So now it's going to be the second row, first column instead of the first row, second column. Sounds complicated, but all we're really doing is flipping everything over that diagonal. So the 2 maps to here. This 3 is going to map down to here. So that first row became the first column. Second row is going to be the second column. Third row is going to be the third column. Okay, so just flipping along the diagonal, what happens on the diagonal? The diagonal stays the same. So next time we're going to talk about some of these transpose properties. You should really read through them real quick. The only one that's really tricky, these are going to be what you expect them to be. The multiplication is going to be a little tricky. Because what we're going to do when we transpose things is we're going to flip the order of the multiplication. So it's going to look a little weird. We'll talk more about that next time. The last thing I do want to comment about is some warnings here. Some special warnings because of this lack of commutativity. So because we don't have commutativity, we're going to have some weird things. If A times B equals A times C, that does not necessarily mean that B is equal to C. Hold Well, why not? Well, because normally to show that B is equal to C, you just divide both sides by A. But what does division mean? We don't have a definition for that thing. That's going to be a problem. Same thing here. AB is equal to 0 for numbers means A is 0 or B is 0. One of those two is 0. Not for matrices, not necessarily for matrices. Well, why not? Well, these are numbers. I would just divide one, by A. I would get B equals 0, and that would work. But here we can't do this. Here we don't have this thing called division. Well, what is division? If I have this thing, 3x equals 6, we like to say that we divide both sides by 3, but really we don't. We have a special property that says there exists an inverse of multiplication. There exists something called 1/3, and 1/3 times 3 gives me the multiplicative identity 1. So I can say that's true. That's what happens when I divide both sides by a number. I'm really not dividing, I'm multiplying by the inverse. So now we have to ask ourselves, can I do that with matrices? So the question is there something called an inverse, where if I take an A, can I multiply it by this inverse thing to get to identity? So that's the question. Is there a matrix like that? And that's what we're talking about next time. Is there an inverse matrix? Turns out sometimes there is, sometimes there isn't. And that's actually true of functions as well. Sometimes we have an inverse function, sometimes we don't. And we can describe when we do in terms of 1 to 1 and onto, and that's how we're going to tee off for the next time. All right, so that's all I have for today. We'll recap a little bit this next time, and then we'll get into 2.2.